c1 e to the minus t, 1 minus 1, there's my eigensolution, plus c2, and I'm going to pull out the e to the minus t because it's annoying not to, e to the minus t, and I got like a 1 plus t for my first component, and I've got a minus t for my second component. Now, if you want to be, one way to look at this is this gives us a way to derive the solution to this problem, right? By solving this problem, we've actually solved y prime prime plus 2y prime plus y equals to 0 in a new way. What does this matrix solution say? It says that x1, which by the way is equal to y, right? Tracking back where we started from, that's equal to c1 e to the minus t plus c2 e to the minus t times 1 plus t. Now it's not very pretty, but there you go. That's the repeated root case. You can also derive the repeated root solution by the matrix exponential and generalized eigenvectors. I personally find this to be the most natural answer to where the t comes from in the repeated root case. That's too strong. It's an answer I like anyway. We've seen other answers, but any questions? Let me repeat what happens. Number one, you look for all the eigenvalues you can. Find all the eigensolutions you can. If that's not enough, then you go hunting for these things. They're always there to find. And you can always find enough of them to make the rest of the solution. That's all that I'm saying. All right. What's that? Am I what? Number 2. I said, was I listing things? Uh-oh, number 2. Oh, man. I don't remember what it was. Oh, no. I mean, we could talk about the complex case, I suppose. Since you brought it up. No, I should behave. So, so that brings us to the non-homogeneous problem. Well, I guess I'll talk about that another day. Let me just do more of this. We should come back to this. I should let this sit. I should do the non-homogeneous problem because if I talk about this another day, it'll help you more. So the non-homogeneous problem. We want to solve dx dt equals to ax plus f. Where f is possibly non-zero, it's some vector of functions. Now, we've had f equals to 0 in everything we've been doing up to this point. How do you solve this? So let's let x be fundamental solution matrix. All right. Which means what? dx dt is what? Is ax. So it's the fundamental solution matrix to the corresponding homogeneous problem. All right? And then what we're going to do is we're going to propose that our particular solution be formed by x times some vector of unknowns, v unknown functions. In other words, v is your parameter. We're doing variation of parameters for systems is what this is. So if that's going to be my particular solution, it has to solve the problem, right? It has to solve star. So what do we do? Plug the particular solution into the differential equation. What's that give us? That gives us, we want dxp dt. It's supposed to be equal to axp plus f. What's that interchangeable with? That's interchangeable with d dt of xv being equal to a times xv plus f. Now, can we simplify that? Well, yes. This is the same as dx dt v plus x dv dt. What am I doing? I did the product rule. This is the product rule for, that's really on there. The product rule right here, if you have the derivative of the product of two matrices of functions, there is in fact a product rule. It's a natural thing. It's you know, if you have a ddt of two matrices multiplied together like AB, it is actually just this. This is your product rule. You got to be careful to keep the ordering of things the same, but that's it. By the way, a column vector is just a special case of a matrix, so this specializes to V being B and X being A. Although A is an unfortunate letter to use there. Here, I'll put a tilde on it. This has no relation to the matrix of coefficients that I was talking about. Sorry. Okay, so what did we say about dx dt? Right? So, in fact, this piece and this piece are the same, right? So these cancel. And we're just left with x dv dt equals to f. And how do we solve? We can solve for dv dt. How do we do that? So multiply by x inverse. How do I know x inverse exists? But that's the identity matrix because x is invertible, right? It's a fundamental solution matrix, which part of the fine print here is that x inverse exists, right? So this gives me that dv dt is equal to x inverse times f. And how do you solve for v? Integrate, right? So v is the integral of, let's say, x inverse of f dt. So in total, we get the following formula. The particular solution is nothing more than our fundamental solution matrix, all right, times the integral of x inverse f dt. Now, if I want to be more precise, I could write like this. I could say xp of t is equal to your initial condition, x naught plus x of t, the integral from 0 to t of x inverse of u, f vector of u du. There would be a solution which builds in the appropriate initial condition. This gives this actually wouldn't be xp, this would be the general solution with x of 0 equal to x naught. This is a solution to the initial value problem. What happens when you put t equals to 0 to the integral? You get integration from 0 to 0, right? So that vanishes. And otherwise, if you differentiate this, the fundamental theorem of calculus for line integrals, it gives you back that this is just x of t times that, which this, I mean, when you differentiate this, it will reproduce just the f of t. anyway, this whole construction showed that that was a solution. So that's how you solve the non-homogeneous problem. You might ask, so undetermined coefficients, right? We spent a lot of time on the annihilator method and undetermined coefficients for the nth order problem, right? Does that happen here? Not in my course. Like, I don't like that section. It's weird. The algebra for undetermined coefficients for systems, it's just unpleasant. This is a general method, and it works for all the problems we're interested in. So this is the way to go. I pretty much will only test you on 2x2 problems because that's the place we can actually find the inverse of the fundamental solution matrix, right? So we'll work one of these another day. I'm not going to try to squeeze it into the last 3 minutes. What I can show you in the time that remains is another fun little fact about fundamental solution matrices. Suppose you have 2 of them. All right? Suppose that x of t and y, well, let's just suppose x and y are fundamental solution matrices of dx dt equals to ax. Right? How are these related? Well, if you think about it, if we think about y being, say, y1, y2, yn, right? And if you think about x being x1, x2, xn, then any one of these columns in either one of the matrices can be built uniquely as a linear combination of the columns of the other matrix. In other words, I can find, I can write any y sub j, I can write it as a sum I equals 1 to n of c sub I x sub I. Why can I do that? Because these are made of solutions to the system, right? And the fundamental existence theorem says that if you have a fundamental solution set, you can build any solution as a linear combination of the fundamental solutions, right? So I means I can build any y vector as a linear combination of the x vectors. Not just that, it's unique. So if you put this together, if you do this for each one, let's see here. Well, I'm about out of time, but after a little bit, you get that y is equal to some matrix times x. So this is the relation. There has to be some constant matrix where this is a constant invertible matrix. Why would this matter to you? I've asked you to calculate the matrix exponential, right? That's a solution matrix, right? So if you think about this as it applies to the matrix exponential, you've got e to the ta, right? It's some matrix that's a constant invertible matrix times, say, suppose you can find other solutions, right? So if you can find these, right, then they're related to the matrix exponential according to multiplication by some thing. So what does that mean? Plug in t equals to 0, what happens? I'll leave some mystery here. This is useful for calculating e to the ta. This is usually the question on the test that people can't do in the past. Anyway. Oh, I'm out of time. I'm sorry. Well, more some other day.